Dear students, welcome to another session of Nuclei chapter. Today we will be going to see about radioactive decay constant. Okay, it is one of the important thing which we have to study in this chapter. So before going to study about the radioactive decay constant, we have to check something with the previous decay law. Okay, radioactive decay law, we have to see about that. Then we can go to the definition of decay constant. So from this radioactive decay law, we have n is equal to n naught e to the power minus lambda t. Okay, this is the statement. Now if we substitute t is equal to 1 by lambda in this equation, we can get n is equal to n naught e to the power minus lambda divided by lambda. Okay, then you know, right, lambda divided by lambda will be 1. So what we can get, n is equal to n naught e to the power minus 1. This minus 1, it is nothing but it denotes n is equal to n naught divided by e, correct? So minus to the power minus 1, meaning of that it is nothing but 1 by e. So we will write e over here. What is e here? E is a exponential constant. So e has got the value 2.781. Now we will substitute this value of e over here. Then I can write n is equal to n naught divided by 2.781. Then we will divide 1 divided by 2.781. What we get here, it is 0.37. Then this previous equation can be written as n is equal to 0.37 n naught. So this 0.37 times n naught, that means n is equal to 37% of n naught. See here, n is nothing but 37% of n naught. The meaning of this is nothing but the definition of decay constant. So meaning will give rise to the definition of decay constant. Decay constant of a radioactive substance is a reciprocal of time, okay, during which the number of atoms left undecayed in the sample reduces to 37% of original number of atoms in the sample. See, this is the definition. See here, we can say it is a reciprocal of time. That's what I have taken here. See, decay constant is a reciprocal. If I want lambda, I can write 1 by t also, right? So decay constant of a radioactive substance is the reciprocal of time during which number of atoms left, see, number of atoms left in the radioactive substance reduces to 37% of the initial value. Okay, so during that time, that is decay constant, reciprocal of time during which the number of radioactive substance in the sample reduces to 37% of the original number of sample. So you can remember this definition. It might be asked for 1 mark. Okay. Then greater the value of decay constant, greater is a rate of disintegration. So you know what is rate of disintegration? It's a time during which the original number of substance reduces to the number of substance at a particular time. So when we have greater the value of lambda, greater will be the rate of disintegration. Then also we can give lambda is different for different radioactive substances. So all the radioactive substances will not have same value of decay constant. Okay. Next we will move on to another topic, half-life of radioactive substance. See, Rutherford was the one who introduced this concept of half-life. So you can just understand what is a full life. So if you consider our life, so we will live up to certain age, right? But you should also remember from the radioactive decay law that the particle will not disintegrate completely. But still we are taking an average. Then we can say full life is nothing but substance completely disintegrates, even though it is not possible. Then half-life means half of the radioactive substances disintegrate. Correct, right? Or you can also say that it is a time taken to reduce the activity of the substance to half of the initial value. Okay, I have written the definition over here. It's a time required for one half of the radioactive substance to disintegrate, and it is denoted by T half. Okay, half-life is denoted by T half. Now we will get an equation. This is an important question actually. We will get an equation of half-life with respect to decay constant. For that, again we have to consider the radioactive decay law, where we are considering initially there are n number of atoms, okay, when time t is equal to 0. Then number of atoms left after time t is n. Correct, right? From the statement what we have seen there, we can write n is equal to n naught e to the power minus lambda t. Now what is the time actually? This time t is nothing but half of the original time, right, required for the complete disintegration. So I'll take this t, that is equal to t half, and when t becomes t half, what happens? The number of atoms reduces to half of the initial value. Then I'll take n is equal to n naught divided by 2. Then we can substitute these values, okay, over here. Then we will write n naught divided by 2, that is equal to n naught into e to the power minus lambda into t half. Okay. Now we can cancel n naught is right, because both are there in the numerator. What we get after cancelling this? We can get half is equal to e to the power minus lambda into t half. Okay, half is equal to minus lambda into t half. Then we will just reverse this equation. Reversing means we can divide it by 1 if you need. Otherwise, just take the denominator term to the numerator. Then I'll get 2 is equal to, what happens to this minus sign? It actually vanishes. So e to the power lambda into t half. We will take log on both the sides. Okay, by taking log on both the sides, what we are going to get, that is log to the base e 2 is equal to lambda t half. So this exponential term vanishes when we take log. Then log to the base e2, I can write it as, so let me give an idea, like what is log to the base e. Log to the base e, it is nothing but 2.303 log to the base 10. So log to the base e is also written as ln. Okay, in physics you must be going to see about this equation or notation for log to the base e, that is also ln. So this value is nothing but log to the base e 2 is nothing but 2.303 into log to the base 10 2. So this value will be multiplied by log 2. We are going to get 0.693. If you want, you can check with your log table. Then I can write for this equation, I'll take this term to this side. Then t half can be written as this one, log to the base e 2 divided by lambda. This value we got here, that is nothing but 0.693. I'll substitute it over here. Then t half is equal to 0.693 divided by lambda. Okay. So what does this equation indicates? It indicates that the half-life and decay constant are inversely proportional to each other. If I want decay constant from this one, what I can do is 0.693 divided by t half. So I can just interchange the position of these two terms. This type of equation, this equation will be used in solving problems related to that. Okay, you have in your syllabus. Now we will move on to the next topic, that is mean life of radioactive substance. So you have come across the word mean. Okay, it is actually related to the average. When you take the reading in your physics, we will take all the readings added together, then divided by number of readings. Very similar, okay, the same thing what we see here also. It is the sum of lives of all the atoms in the substance divided by total number of atoms present initially. You have to add the life of all the atoms together, then you divide it by total number of atoms present. We have only about the definition and an equation related to this. Okay, so we can see the equation for this mean life, that is nothing but we denote it by tau average, that is equal to 1 by lambda. Okay, mean life is reciprocal of decay constant. If you want to find out this mean life, you can just divide the decay constant value like 1 divided by decay constant. So you are going to get mean life. Let's check the duration between mean life and half-life. So half-life is given as 0.693 divided by lambda and mean life is given as 1 by lambda. So from this equation we can write lambda is equal to 1 divided by tau average or mean life. Okay, we will substitute it over here for lambda. What happens then when we substitute t half, that is equal to 0.693 divided by, see, 1 divided by tau average. So 1 divided by tau average means this term goes to the numerator and we can get t half is equal to 0.693 tau average. Okay, we will see about activity now. So activity I have already mentioned, it is a rate of disintegration in a radioactive substance. Okay, so whatever we have seen in the previous one, it's a very similar thing. Activity, it is also the rate of disintegration in a radioactive substance. So activity can be written like A is equal to minus dN divided by dt. Why? Because activity is nothing but rate of disintegration from the law of radioactive decay. So A is minus dN by dt and also it is nothing but lambda n. So negative sign shows that activity decreases with the time. I can write A is equal to lambda n. Then what is n? N is nothing but n naught e to the power minus lambda t. Correct, right? We will write it over here. Then what is lambda n naught? See here, lambda n is nothing but A. Then lambda n naught can be written as A naught. Now we can write the activity A is equal to A naught e to the power minus lambda t. Okay, so this is a equation or the equation for the activity. Now we will see some of the units which we need to express the activity. So activity can be expressed in following unit. First one is Becquerel, next one is Curie, next one is Rutherford. So these are the 3 units with which we express activity of a radioactive substance. We will see Becquerel first. Becquerel is a SI unit. Remember, Becquerel is a SI unit of activity. So 1 Becquerel, okay, 1 Becquerel, it is nothing but 1 disintegration per second. Okay, 1 disintegration per second. Now, what about Curie? It is the next unit. It is not the SI unit of activity, but you can express this Curie in terms of Becquerel. So, activity of a radioactive substance is said to be 1 Curie if it undergoes, see here, 3.7 into 10 to the power 10 disintegration per second. See, if the activity of a particular substance is said to be 1 Curie when it undergoes 3.7 into 10 to the power 10 disintegration per second. So we can write 1 Curie, that is nothing but 3.7 into 10 disintegration per second, or what is 1 disintegration per second? It is nothing but Becquerel. So we can write 1 Curie is equal to 3.7 into 10 to the power 10 Becquerel. So this is a relation between Curie and Becquerel. So you might get this question for maybe 1 mark. Okay. Next one is about Rutherford. Rutherford is another unit of activity. So activity of a substance is said to be 1 Rutherford when it undergoes 10 to the power 6 disintegration per second. Remember, for Curie, how many disintegration it has to undergo? 3.7 into 10 to the power 10 disintegration, but here in terms of Rutherford, it has to undergo 10 to the power 6 disintegration. Then we can write 1 Rutherford is equal to 10 to the power 6 becquerel. So in terms of out of these three units, Curie is the biggest unit and becquerel is the smallest unit. Okay, so becquerel is the SI unit of activity and these two are the other larger units. Like what you have, meter is a SI unit of length, but you express in terms of kilometer and you express in terms of centimeter, millimeter, like that. Okay,